In this section, we explain how to calculate the reaction forces. When a triangularly distributed vertical action force acts on a cantilever beam, a cantilever beam is a statically determinate structure with 3 reaction forces and no intermediate hinges. Therefore, all reaction forces can be determined using the equilibrium conditions in 3 directions. For an object at rest, equilibrium in all directions must be satisfied. The cantilever beam, we will discuss, has a free end at point A, a fixed support at point B, and a length of L, as shown in the figure. We will determine the reaction forces when the triangularly distributed vertical action force, W, acts on the beam. Steps for determining reaction forces. Step 1. Create a free body diagram of the reaction forces. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. Step 1. Create a free body diagram of the reaction forces. For a beam, a free end allows movement in all directions, vertical, horizontal, and rotational. A roller support allows the beam to move freely in the horizontal and rotational directions, but restricts movement in the vertical direction. A hinge support allows the beam to rotate freely, but restricts movement in both the vertical and horizontal directions. A fixed support restricts movement of the beam in all directions, vertical, horizontal, and rotational. The free end, at point A, allows for movement in all directions, so there are no reaction forces acting in any direction. The fixed support, at point B, restrains vertical, horizontal, and rotational movements of the beam, so the reaction forces at point B are the vertical reaction force VB, which restrains vertical movement, the horizontal reaction force HB, which restrains horizontal movement, and the reaction moment MB, which restrains rotational movement. The directions of the reaction forces are assumed as follows. VB is upward, HB is leftward, and MB is clockwise, as shown in the figure. Note that the symbol for the reaction moment, shown in the free body diagram, uses the same notation, M, as that for an action moment. Therefore, it is necessary to analyze whether the M symbol in the free body diagram represents an action moment or a reaction moment, and to proceed with the analysis of force equilibrium and other related analyses accordingly. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. the distributed action force, W, is the force per unit length, so its unit is not Newton, but Newton per meter. Therefore, the distributed action force, W, cannot be directly summed as a force. As we proceed with summing forces in moments, it is necessary to replace the distributed action force, W, with the equivalent force. Let's identify the three components of the force due to the distributed action force W in the figure. The magnitude of the force due to the triangularly distributed action force W is, like that of a uniformly distributed action force, equal to the area of the right triangle, formed by W and L, in the figure, which is W multiplied by L, divided by 2. The direction is downward, and the point of application along the beam's axis is at the centroid of this right triangle. Which is point C in the figure. We will now analyze the equilibrium of forces in the vertical direction. Refer to the free body diagram of the reaction forces for the vertical forces. The vertical forces are the action force, W multiplied by L, divided by 2, at point C, and the reaction force VB at point B. We will derive the equilibrium equation for these forces. In the vertical force summation, forces acting upward are considered positive. Let's clarify this. The action force, W multiplied by L, divided by 2, acts downward, so it contributes minus W multiplied by L, divided by 2. The reaction force VB acts upward, so it contributes plus VB. To achieve equilibrium of these vertical forces, the algebraic sum must be 0. This concludes the discussion on the vertical forces. We will now analyze the equilibrium of forces in the horizontal direction. Refer to the free body diagram of the reaction forces for the horizontal forces. The only horizontal force is the reaction force, HB, at point B. Since HB is the only horizontal force, the equilibrium equation can be expressed as follows. We will now analyze the rotational equilibrium of moments. First, examine the lines of action for all forces. The lines of action are as follows. The line of action for W multiplied by L, divided by 2. The line of action for VB. And the line of action for HB. To determine the magnitude and direction of the moment caused by a translational force, it is necessary to have information about the arm length relative to the center of rotation, which is calculated from the force's line of action. In contrast, the reaction moment mb in the figure already has the defined magnitude of mb and the clockwise direction. Therefore, the concepts of line of action and arm length, are not necessary for the moment. Next, select the center of rotation. Choosing the point, through which, as many lines of action of the unknown reaction forces, pass as possible, will simplify the calculations for determining these reaction forces. In this case, we will select point B, through which, the lines of action of the unknown forces VB and HB pass, as the center of rotation. Then, calculate the shortest distance, from each line of action, to the center of rotation at point B. This shortest distance will serve as the moment arm length for each force, relative to the center of rotation. The arm length for the action force, W multiplied by L, divided by 2, is the 1/3 of L. Since the line of action for the reaction force VB passes through point B, the arm length is 0. Similarly, the line of action for the reaction force HB also passes through point B, so its arm length is 0. We will derive the equilibrium equation for these moments. In the summation of moments, clockwise moments are considered positive. The center of rotation is point B. Let's clarify this. The action force, W multiplied by L, divided by 2, acts counterclockwise, so it contributes minus W multiplied by L, divided by 2, and multiplied by the 1/3 of L. Since the arm length of the reaction VB, with respect to the center of rotation, is 0, its contribution is 0. Similarly, since the arm length of the reaction HB, with respect to the center of rotation, is 0, its contribution is 0. The reaction moment, MB, acts clockwise, so it contributes plus MB. To achieve equilibrium of moments, the algebraic sum must be 0. This concludes the discussion on the moments. The reaction forces, VB, HB, and MB, are determined through the equilibrium of forces in 3 directions as follows. The signs of these forces are based on the free body diagram shown on the left. The positive sign of VB indicates that this reaction force acts upward, which is consistent with the vector assumed in the free body diagram. Since HB is 0, there is no direction associated with it. The positive sign of MB indicates that this reaction moment acts clockwise, which is consistent with the vector assumed in the free body diagram.